Okay, good afternoon, everyone. Welcome to the first TAMIDS senior series for the fall semester. Today, our senior speaker is Dr. Chih-Li from Michigan State University. He is an assistant professor in the Department of Statistics and Probability. Chih-Li's research area includes the analysis of various problems and certain computation, the big data, and the statistics in engineering, machine learning. He will talk about multi-fidelity computer experiments today. So welcome.
Thanks for the kind introduction. That's been great for inviting me to come over. It's really my pleasure to be here today. So today I'm going to talk about one of my research works on multi-fidelity simulations. Okay, so let me just good. All right, so the proposed design more specifically is called stacking design, which is used to design multi-fidelity computer experiments, or more generally, multi-fidelity simulations with target predictive accuracy. So I'll talk about this target predictive accuracy in a few minutes. And this is a joint work with Professor Simon Mack at Duke University, and his two students, Irene and Tom. Good. Right. So let me get started. Okay. All right. So this is the agenda for today. I will first introduce multi-fidelity data, and I will use an example to show you the challenge the problem is, and we'll move on to our proposed method. To explain this method, I have to talk about the model we are going to use for these multi-fidelity simulations, and I will show you some error analysis for this statistical model, and then we'll move on to this stacking design. And I will use an example to show you how this method works. And more importantly, I would also like to show you this cost comparative theorem, which I think is one of the biggest contribution in this work. All right, so lastly, I'll give you a quick conclusion. All right, so what is multi-fidelity simulations? So computer models has been commonly used to understand real-world features, phenomena, and or events. So as we know, those physical experiments could be very, very expensive to run, to implement. So computer models has been commonly used to understand those invisible phenomena. Especially nowadays, those computer resources are quite powerful. So those computer models can be solved by computer simulations, by those numerical methods such as finite element method or finite difference methods. And in those simulations, you could either have very high fidelity simulation, which is very costly, but close to the truth. So I'll talk about this truth later on. Or you could have low fidelity simulation, which is cheaper, but less accurate, right? It's not as accurate as high fidelity simulation. Of course, you could have some intermediate fidelity simulations. So let me just show you one example. This is a motivated example in this study. So we like to study the thermal stress of jet engine turbine blade, which can be analyzed through a static structured computer model. And this model can be numerically solved by finite element methods. So in this study, we have two input variables of interest. One is pressure, one is suction. And this is how the simulation looks like. This is the simulation output, which is a 3D image. And in this study, what we are interested in is the average of this thermal stress. Okay. So in this example, if I have pressure equal to 0.23 and the suction equal to 0.71, I have this 10.5 as our output. Of course, if you want to simulate, if your output is 3D image, there will be more challenging. But as a starting point, we focus on this average of thermal stress as your state scalar output. All right. So what we are interested in is, oftentimes those engineers want to explore the input space. For example, we want to try different pressure value and the suction value. Of course, you can run this simulation, but the simulation takes time. It could take hours, it could take days, it could even take weeks to run these very high fidelity simulations. So it's not practical to try different input locations and get your results and then see which one is the best. So as a statistician, what we can do is to build a so-called surrogate model, or more generally, it's just a statistical model that can mimic the relationship between X and the response. All right. So how do we build this surrogate model for this problem? Well, we could find a statistical model that can leverage low fidelity simulations and high fidelity simulations. So let me show you this example. Given this input variable, given this input location 0.5 and 0.5, we could have 3 different fidelity of your simulations. So how do we tune this fidelity? In finite element method, the most straightforward way is just to change the mesh size, the mesh configuration. So you see that here, in this finite element methods, we have very dense mesh configuration. So the mesh size is pretty small here. And it gives you very accurate solution. But the price is that it's going to be very computationally expensive. So on the other hand, we can try this low fidelity simulation. You see here, the mesh density is pretty coarse. It's pretty coarse. So the mesh size is pretty large. This computationally is much faster than this high fidelity one, but it's less accurate, right? So this is another example. You see here, the high fidelity simulation can capture some detailed behaviors, but you see this low fidelity only can capture these general outputs, general behaviors. All right. So we want to build a surrogate model or statistical model that can leverage those high fidelity simulations and the high fidelity simulations. So this is our objective. Can we leverage both low fidelity and high fidelity simulations in order to, first of all, maximize the accuracy of prediction? And also we want to minimize the cost associated with these simulations. If my objective is only maximize this accuracy, then I can pretty much just run high fidelity simulations and build a statistical model. But it's going to be costly, so while we want to maximize the accuracy, we also want to minimize the cost, computer cost associated with those simulations. So the goal here is to build a cheaper statistical model that emulates the model outputs of these high fidelity simulations based on the simulations with multi-fidelities. So we call this emulator or surrogate model. So this is the idea. The statistical model leverage these 2 fidelity or most fidelity simulations, and we emulate the output of high fidelity simulations. Okay, so before I move on, I would like to first introduce some notation. It's not too much. So here, you see here, we have fidelity 1, 2, 3. So the high fidelity is the solution, the more accurate the solution is. So in this case, F3 is the highest fidelity simulator, and F1 is the lowest fidelity simulator. And we have 3 different mesh sizes in this example. So this is, this high fidelity has the smallest mesh size, but this low fidelity has the highest mesh size. The cost is denoted by C1, C2, and C3. And as you can imagine, this high fidelity has the highest cost. Right. So that's the only notation I need for this talk. So let's talk about existing methods. So there are 2 most common popular approaches. One is this autoregressive model or co-aggregate model, which was proposed by Kennedy and O'Hagan in 2000. And there are many applications using this model. All right, so the idea is that I have this low fidelity simulator and I have this high fidelity simulator then I just built this relationship using this rule and this discrepancy function. So this Z describes the discrepancy between the high fidelity and the low fidelity. And they just assume those unknown functions as Gaussian process priors. So Gaussian process priors has been commonly used to model those unknown functions under a Bayesian framework. And people have found that it works pretty well. Another also very popular approach is this non-stationary Gaussian process, which was proposed by Professor Tuo and Wu and Yu in 2014. Their objective is a little bit different because they want to emulate this so-called true solution when this mesh size goes to 0. I think ideally this is what we want to emulate, right? Because if you look at this, well, here you have this very small mesh size, and then you claim this is high fidelity simulation. But you never know this mesh size is small enough, right? So in reality, what we are interested in should be when mesh size goes to 0, then how the solution looks like. Although this is not feasible because you cannot make your mesh size really equal to 0 and run a simulation. It's not possible. But that should be what we are interested in, right? So in this study, we are also trying to emulate this true solution when the mesh size goes to 0. Okay, so from design point of view, I think this nested spacing design has been commonly used in the literature. So the idea is that if you have higher fidelity, the input locations of these high fidelity simulations should be nested with these low fidelity ones. Right? So for example, here, this X1 is the input location of low fidelity simulations, which have, I don't know, 7 points, no, 8 points. And for these high fidelity simulations, I have those input locations, these 4 points, and those data should be nested. So the advantage of doing this is that make your computational easier, more efficient. All right, so those approaches are very promising, but I think there are some important questions that have not been answered. First of all, what is the sample size for each label? Right, suppose I have 5 different label simulations. How do I decide those sample size for those simulations? So of course, if I want to increase the accuracy of my model predictions, I can just spend all of my budget on high fidelity simulations, but it's just going to be very costly, right? So we have to determine these sample sizes by accounting for your computational cost of each fidelity simulations. Right. Second question is, how many fidelity labels should we use? Well, in the previous example, I was using 3, right? How do we know these 3 fidelities are the optimal ones we should use? Right? And related to the question 2, how do we decide the mesh sizes? So in the previous example, I showed you 3 different mesh sizes. Are they optimal? And can we find what if I have a new label of the simulation? What is the mesh size I should use? Last but not least, is multi-fidelity simulation really better than multi-fidelity simulation? Sorry, single fidelity simulation. So, like I just mentioned, maybe we could just spend all of my budget on single fidelity simulation. I just spend all of my budget, all of my time on this highest fidelity simulation. I don't want to run multi-fidelity simulation. Would that be better? Well, typically, like statisticians want to have more and more data to get a good model, right? But is that always the case, especially in the context of multi-fidelity modeling? In fact, I will show you in some cases, this is actually wrong. Multi-fidelity simulation is actually sometimes worse than single fidelity simulations from that point of view. In some cases, you should just spend all your budget on single fidelity simulations. Right, so I will talk more about this later. Any questions so far? All right, so let's move on to the methodology. But first of all, I need a model to leverage those multi-fidelity simulations. Recall that the objective here is to emulate these 2 solutions. Okay, so the idea is that for this high fidelity simulator, it can be decomposed into those components. Each component represents the difference between these two fidelity simulations, right? So this, well, F0 will be 0. So this is just the lowest fidelity simulator, and this is the second fidelity and the first fidelity difference. And we assume the data is nested. All right, so the reason we like to make this assumption, or we like to have this assumption is that, given this assumption, we can actually evaluate the outputs of each component. For example, here, since the data is nested, we can actually evaluate the difference between these two simulators. So for example here, because I have the output here for low fidelity and high fidelity, and I have the output for low fidelity and high fidelity. So actually I have these 4 outputs for these differences, this difference. Right? So I can evaluate these outputs based on this nested assumption. So we use this reproducing kernel hyperspace interpreter for each component because you have data, this observed data, then this reproducing kernel hyperspace interpreter just like this, with this kernel, this positive definite kernel function, right? And then you can build your multi-level interpreter by sum over those interpreters. Okay, so this is the model I'm going to use. This is the head will be used to predict the output of the highest fidelity simulation. Okay, so let me specify this kernel function. So in this study, I'm going to use this merton kernel, which is commonly used in computer experiment and spatial statistics literature. So in this kernel function, we have this smoothness parameter, length scale parameter, and the scale parameters. So this smoothness parameter controls the smoothness of the function you are going to fit. And those parameters can be either estimated by this cross validation or maximum likelihood. So how do we use maximum likelihood? We can use a Gaussian process prior assumption, but let me talk about this in the next slide. So alternatively, you can actually assume this ZL to follow a Gaussian process prior, okay? Because the prior mean, the posterior mean is actually equivalent to the interpreter that I just showed, okay? But just to rigorously develop the theoretical properties later on, I'm gonna just use this RKH as interpreter for developing the theories. Okay. Right. So if you assume those are Gaussian process priors, then it's just a special case of Kennedy or Hagen, those coherent model that I just showed in the previous slides. All right. Any questions about this? Yeah.
In the previous slide, I was on one. How would you describe the difference between single and multi-fidelity exactly?
Yeah, so here so this model is for multi-fidelity. Right? Right, that's a good point. If I have only single fidelity simulation, then I'm not going to use these differences as my observations. I'm just gonna, for example, I can observe this L, this data from these outputs, just single function. Then I can just build an interpreter just using this observation. In fact, I will denote this interpreter data, single fidelity interpreter data. Thank you. Any other questions? All right, so we have this interpreter as our model to predict those model, to predict the simulation output. So let's develop some theory here. Recall that our goal is to emulate these two solutions, right? So this error, between these two solutions and your interpreter actually can be bounded by this. So there are two terms. So one is simulation error. So the simulation error is that, well, even your even you are using this single fidelity simulator, right? Your simulator is not going to be perfect because you cannot make your mesh size equal to 0. So you always expect there are some errors using this single fidelity simulator. Another term is emulation area because we have finite samples. So your interpreter it's not going to be perfect. Of course, you have more and more samples, you can approximate these two solutions pretty well. But the thing is, two function of L will be very good. But the thing is, you don't have an infinite sample size. So you also expect some uncertainty here. So you have two uncertainties here. So I think in the context of statistical learning, this could be interpreted as bias and variance. So this is variance caused by your finite samples. This is the bias of your simulator. Okay, so we have this. Remember that my title is talking about this targeted predictive accuracy. So what we are gonna do is to make sure my interpreter has an error that is smaller than this desired accuracy epsilon. So this is why we call that with target predictive accuracy. Right? So this is our goal. We want to make this error smaller than a desired accuracy. So you can pre-specify your accuracy beforehand before you do your analysis. So I will show you an example later on. So this norm could be L2 norm or infinite norm, uniform norm. I'm sorry, uniform. Okay, so by doing so, to do so, we can just make the simulation error smaller than half of epsilon, and also make this emulation error smaller than half of epsilon. And by doing so, this can determine the number of fidelity level you should use. And by making this smaller than half of epsilon, you can determine the sample sizes. All right. Then this forms our stacking design. So this is our main idea in this work. Any questions? Yeah.
Is the choice to divide by 2 here arbitrary? Because it seems to me if L was very large, then the first term would be you could make epsilon divided by n very small. And then the other one, you just get arbitrarily large number of sample sizes.
Yeah.
And so the solution is do lots of high fidelity simulations.
Exactly. Good point. So here we just provide a general rule, but you are right. This is bias variance, right? So you can decide where you want to make this bias smaller or make this very smaller. So yeah, this can be user specified. Any questions? All right. So let's first talk about how we control this emulation area so that we can determine this sample size. So this that relies on this proposition. So we first show that this emulation area can be bounded by this upper bound. So suppose that this input space is d-dimensional and is bounded and convex. We assume this design for each fidelity level, for each simulation is constant uniform. So you can imagine this constant uniform is just some space-fitting design. You just assume your design is quite space-fitting. We have this sample size N. And we have this nice result where this norm is native, this RKHS norm. Right. So you can see that the bound also depends on this smoothness and the scale parameter. So I have the definition of this uniform as constant uniform design, but you can just imagine this is a space-fitting design. Okay, so with this upper bound, we can actually determine the sample size because, of course, when we want to make this emulation error as small as possible, so we can just minimize this upper bound and account for the computer cost. So this term is the total cost of your simulations, right? Remember, each simulation, each fidelity has an L sample size, and this is the cost of each fidelity simulation. So we can just use this Lagrange multiplier to minimize this whole thing, and it gives you this nice form of these optimal sample sizes. Okay, So you can see it actually makes sense because this CL, if the cost is larger, then of course you are going to have smaller sample size. You cannot really spend too much budget on this fidelity if it's too costly. And the rate is array depends on the dimension of your input as well as the smoothness of your function. However, here we have this constant that is unknown. Right? One approach, one strategy is to have a total budget. Suppose your total budget is 1,000 seconds, or I'm sorry, 1,000 hours. You can determine this mu very easily. But recall that our goal here is to make your error smaller than half of epsilon. So we need another strategy to make this happen. So how do we make this happen? Well, we use another bound. So the reason we use this bound is that they don't have any constant here, unlike the bound that we showed here. So we have this power function. So let me skip the details here, but this power function depends on the mu constant that I showed before. So we can just draw a line to show the relationship between this bound and the mu, and make sure this bound is smaller than half of epsilon. Then we can determine this new star. So I skip many details here, but I just want to make you know that we can determine this new star by making this smaller than half of epsilon. Okay, so this is how we control the emulation errors and how we determine these optimal sample sizes for each fidelity level. So let's move on to the second question. And to answer the second question, we need to control the simulation error. Okay, so how do we control this one? Well, we use this error rate of finite element method simulations. So this was also used in this paper. Under some regularity conditions, then this simulation error can be bounded by this mesh size with this alpha as the rate. Okay. So here is just an example. I think this example was from this grade. This is another, sorry. All right, so you can see that this is the mesh sizes. So if you increase the mesh size from this value to this value, the simulation error grows exponentially. Right, so you can see that this error is controlled by this mesh size with the rate alpha. Okay, so we are going to use this property to control this simulation error. And how do we do that? We first specify your mesh sizes by these geometry sequences. All right, so we assume the mesh size is half smaller than the previous fidelity mesh size. Okay. So you can actually find that this bound can be written as this. So I skipped many details here, but what I can show is this simulation error can be bounded by this term. Right? So I can just make this one smaller than half of epsilon. Sorry, so here this numerator is unknown because we never know the true function, but it can be approximated by the norm of its interpreter. Okay, and so we are going to find L, the fidelity level that can ensure this error is smaller than this half of epsilon. So we can choose this L to determine the fidelity level by using this. So I will demonstrate an example later on. Any questions here?
So I have a question. So you said the RKHS norm can be approximated by the Gaussian process regression estimate. So that means you have to have some data, but this is Dirac experiment. So what is your
good point. Right. For those work for those methods to work, we have to have some initial data, initial design to estimate those and estimate the parameters in the kernel function. So we don't know those beforehand before we have data. So you're right. We have some initial data and to estimate those values. Any questions? Okay, so let me move on to this. So we don't know this rate, right? This error rate alpha. In 12U, this paper, they determine this alpha according to the quality of interest. So alternatively, you can actually determine this alpha by you collecting the data. But like Professor Chua said, we need to have data to estimate this alpha. So that's another. This is another reason we need some initial data to estimate those values. So I also skipped some details here, but you can see that we can just find the relationship between this, and to find the slope, which is going to be this alpha hat. But the downside of doing this is that you need at least 3 levels to estimate this alpha. Okay, so we have answered these 2 questions. So like I said, we need L that measure to ensure this simulation error is smaller than half of epsilon. And this is how we determine the mesh sizes. Okay, so how does our stacking design work? We start with a low fidelity simulation, just single fidelity simulation, but maybe with large mesh size. Okay, we start with a very low fidelity simulation. And we sequentially increase your fidelity level until this condition is satisfied, until this simulation error really smaller than half of epsilon. So this is how our algorithm works. We start with this very large mesh size, lowest fidelity, and then we find the sample size by controlling this emulation error. And then we detect whether this is satisfied to determine whether the simulation error is really small enough. If not, we increase the fidelity with this smaller mesh size, And then we go back to find their sample sizes again until this simulation error is really bounded by this half of epsilon, and we return our multi-level interpolator. All right, I think it's easier to just use an example to demonstrate how this works. All right, so I'm going to use this turbine data, and we have 2 variables. And again, the output is the average of thermal stress. So we can't really run those simulations with mesh size equal to 0, but I'm able to run some of the simulations with very, very small mesh size. So I'm going to just use them as our test data and to validate our proposed method. So they say I wish to make this L2 error smaller than 5. Again, you have to specify your desired accuracy. So we start with this lowest fidelity with this mesh size, 0.05, which is exactly this, 0.05. Right, it's very low fidelity, very low fidelity, large mesh size. The course is pretty quick, right? So we need to make this emulation error smaller than 2.5, right? We need 13 samples. So those are the 30 samples of this lowest fidelity simulations. So it's specifically designed for quantum uniform design. Those are the 13 simulations. Okay, we can't really compute this simulation error because we are not able to estimate this alpha, this error rate. Like I said, we need at least 3 levels to estimate this alpha. So we increase the fidelity level, then you can see that this is fidelity mesh size 0.025, and the cost is higher. Right, so 0.25 is actually this, right, the second one. And you can see that to make this emulation error smaller than 2.5, we need these sample sizes. For lowest one, we need 4 additional samples. Right, 4 additional samples. And for this new one, we need 10 samples. So this is why we call our method stacking design, because you see those samples stack on the previous samples. So again, we can really compute this simulation error bound. We just increase the fidelity level, and this is small, very small mesh size, half of the previous one. Right? And to make this emulation area smaller than 2.5, we need these samples. So you see here, we need 18 additional samples for this lowest fidelity. And now we are able to compute this simulation area bound, which is greater than 2.5. So the bias is still higher than 2.5. We need to increase the fidelity level. So we make this mesh size even smaller. All right, the cost is much higher now, but that can make sure your simulation error is smaller than 2.5. So now both of the errors smaller than 2.5, then we are happy and return the interpreter. And I compute this empirical L2 norm, L2 error, by using those 20 points, 20 test points, and we got this 2.01, which is smaller than the specified error. Yeah.
Okay, so each of these levels is run independently of the results of the previous level. You select new points for each of these,
Yeah.
and you run some of them at a low fidelity and some of them at higher, and then at the third levels and then the fourth levels.
Exactly.
Certain points are run at high fidelity and certain points are run at low fidelity.
Yeah. Exactly.
Within the pressure suction space.
Exactly.
Okay, how are you selecting the points?
That's a good point. So here, to make this theorem justified, we need this quantum uniform, and it should be nested quantum uniform. This is easy, it's quite challenging, but here we use this low discrepancy sequence. They make our life much easier. Although people say that this low discrepancy sequence, they don't know whether this is quantum uniform yet theoretically, but in practice we found that works pretty well. So we used Sobol sequence to choose those points in two-dimensional space. So those are not probably the perfect specific design points, but they are quite uniform, still quite uniform. Does it make sense?
I don't quite understand what quasi-uniform means applied to the two-dimensional space here. Uniform with respect to what?
Yeah, that's a.
I'm also okay with taking this afterward if you would rather just keep going.
Yeah, sure, but I can quickly explain this quantum uniform. So the idea of quantum uniform is that any 2 points should be greater than smaller. Sorry, the meaning. Gosh, what's that? So any 2 points in your design, the minimum one should be greater than something, right? Yeah, the minimum of any 2 points should be greater than something. So that's called so this distance is called the field distance, and we want to make this field distance as large as possible. So they can make these points look uniform in this two-dimensional space. But yeah, we can talk more in the
Okay, thank you.
Yeah, thanks for your question. Any other questions from the audience? Yeah.
So here, in this slide, you gave a recipe on how to choose the number of points, etc., based on the target accuracy epsilon. Right here. But so you don't know F infinity, correct? Isn't it? So this is an absolute target accuracy. If you have a relative target accuracy, let's say you want F infinity minus FL hat to be less than epsilon times F infinity in now. So you want a relative accuracy. You do something in this situation.
So can you?
So your epsilon is independent of F infinity, right? Since I don't know F infinity, maybe I want a relative error rather than an absolute error.
Oh, I see.
If you have a relative error, can you do something because you don't know F infinity or even its norm?
Yeah. In this case, I don't know if it's easy to derive those error bound.
Yeah,
I think so. Maybe yes. Maybe yes. Yeah. I'm not sure, but I'll think about it.
Predictive model is still reality.
Yeah, maybe. Hey, cool. How much time do I have?
Yeah, 20 minutes.
20 minutes? Okay, I think it should be good. All right, so this is how we estimate this error rate. But let me just quickly, I didn't go into the details, but by those simulation error, we can actually have this property. So the alpha basically is just the slope of this. Okay, so this is our interpreter, multi-level interpreter, and those dots are the test points that I mentioned. Yeah.
In the previous slide, why are you presuming L is greater than or equal to 3?
Yes. Good point. So the reason is that we need to have at least 3 points so that we have two differences, two components observations, so that we can draw this linear regression line. So at least 3. Yeah. Okay, so this is our interpreter. It looks quite close to the truth. All right, so let me show you some theoretical results. So for the sake of simplicity, let me just assume those smoothness of each function will be equivalent. And this simulation error bound is bounded by this. Okay, so this is similar to, it's the same as the previous slide, but I'm using this this geometry sequence measure size. So you see 2 here because I'm using this geometry sequence measure size. Furthermore, I assume this cost is governed by this rate beta. Right? So I think this is intuitive. You will see that this cost actually depends on your measure size, and you have this rate to control this computational cost. And under some regularity conditions, we can make this smaller than epsilon with the total computational cost, which is bounded by this. This looks very complicated, very involved, but you see we have conditions here. What are those conditions? Actually, that makes perfect sense. You see that the first term is actually the to control the simulation error. So alpha is the simulation error, beta is the computational cost of each simulation. The second term, so I'll talk about the second term later. So, sorry, I jumping around. So, when this condition is met, we spend more budget on coarse mesh size. Yeah.
What was C3 in the previous one?
Sorry.
C3.
C3 is just constant.
Okay.
Some unknown constant. Right. So because we are only interested in the rate related to this error. Okay, so in this case, we will spend more budget on coarse mesh sizes. So we spend more budget on low fidelity simulations. If this condition is met, then we spend more budget on most high fidelity simulations. If this condition is met, then we evenly spread those simulations. And if you look at these two conditions these two values more closely, it actually makes sense. This tells us that this is the simulation error reduction over the rate computational cost as fidelity increases. If you want to increase the fidelity level, then this is the error reduction you are going to have. The second term is actually just the rate of the convergence of your interpreter of each component as sample size increases. So like I said, those interpreter is not going to be perfect because you only have finite sample. But if you increase the sample size, this is the rate you are going to increase. The error is going to increase. Decrease. All right, so this gives us some insights about this budget allocation. But I want to show you this comparison between single fidelity and the multi-fidelity using the rate I just derived. So what if we spend all of my budget on single fidelity simulations? Right. recent study have found that, so grading is just GP. People have found that if you use independent GP and use some very complex GP with very complex construction to couple those multi-fidelity simulations, actually you will get worse result than independent GP. So I found this result very appealing, and I want to find out why. And in machine learning community, they often call this negative transfer. So this is saying that, well, if I have some target data, I'm doing some classification approaches, I can get the accuracy 70%. But if you just bring another, they call the source data, and do this classification method together, you can actually worsen your result. Right? The accuracy actually increase from 70 to 60%. So this is often called the negative transfer, and it has been very popular in the machine learning literature. Okay, so let me move on to this. I think to answer your question, so we have this single fidelity RKHS interpreter, which is based on just single fidelity simulation. I'm using this FH to denote this certain fidelity simulation. So I'm using one set of the data. I'm not using multi-fidelity data. And suppose the mesh size is for this high fidelity simulation satisfies this condition, we get this error bound with this total cost, with this rate, right? All right, so how do we compare these two? Well, we can just compare their error rate, the cost rate. So we found out that when this condition is met, this multi-layer interpreter has a slow cost rate. So that means in this condition, multi-fidelity is actually better. You require less computation cost than single fidelity simulation. But in this case, single fidelity is actually better. Right? You should just spend all of your budget on single fidelity. So let me just use two extreme cases, and you will see why this is true. So when beta is very small, so the beta is small, for small beta, that means the cost increases very, very slow. Alpha is large, that means the simulation error decreases very, very fast. So this is the case. Suppose I have 5 levels of simulations. C1, the cost, is almost equivalent to the very high fidelity simulation, 2.9 and 3. But if you look at this simulation error, one is 10 and one is 0.001. So in this case, there's no point to use multi-fidelity simulations. I can just run this F5 for many samples, as many samples as possible, because the costs are almost equivalent. Right, so I think that makes perfect sense. All right, another example is that if we have very small nu, so again, nu is the smoothness of the function. So if you have very small nu to make this condition met, and then that means we have very non-smooth for each component. So this is another extreme case, right? Suppose for high fidelity simulator, it has this underlying function, very, very smooth, very simple curve. But let's say you have this low fidelity simulator like this, jumping around. And their difference is gonna be this, also jumping around. In this case, you need so many samples to get a good approximation, right? For this function, also this function. You need so many samples. So unless these low fidelity simulations are really very, very cheap, then there is no point to run those fidelity simulations. For this high fidelity simulator, this function, I can just use 5 points to get a very good approximation. Right? So this gives us some insights about the comparison for these two. And we see that in some cases, yes, we should just run this single fidelity simulations. But of course, there's a difficulty. You have to determine the mesh size, right, to make this happen, because the rate here depends on the mesh size, which should satisfy this condition. So that's the difficulty in reality. Okay, so we also answered this question. In conclusion, let me just quickly wrap up. So we propose this target design which determine the sample sizes, also determine the mesh sizes, also determine the number of fidelity labels. We also have shown that this cause complexity, which give us some insights on budget allocation and the comparison between single fidelity and multi-fidelity. As well, this is the archive manuscript, and thank you, and thank organizer for supporting this work. Thank you very much.